Good afternoon, everybody. We are still pushing right along. We're going to be finishing up this unit next week. Looking at the schedule, I do believe that we are still on pace for this class to be finished by May the 8th, as anticipated. So we're looking at properties of rational functions today. A rational function is simply a function that is expressed in terms of a ratio of two other functions. And when we talk about this, one of the things that we want to first address is the domain of a rational function. And it's not too difficult to come up with the domain of a rational function. You simply look at the denominator of each rational function and find what values would make that denominator 0, and those are excluded from the domain. Because we already know for all polynomials, the domain is all real numbers. But now we're taking a polynomial over a polynomial, and we have to come up with a way to exclude values, because if the denominator is 0, then the function is undefined. So, and that's really simple to do. So for part A, you just simply take the denominator, and you could write it out as not equal to 0 and solve for x. And what you find is that x cannot be 5. So in terms of notation, you can write that out as all x such that x is not equal to 5. Or you could write it out in interval notation, where you have it's negative infinity to negative 5, union negative 5 to infinity. Part B, you would do it the exact same way. Take the denominator, set it not equal to 0, and solve for x. So we would add the 4 to both sides, and then we would take the square root. Now remember, when you take the square root, that will be plus or minus. So we get that x cannot be plus or minus 2 in this case. So in set notation, it's x such that x cannot be plus or minus 2. In interval notation, it's going to be negative infinity to negative 2, union negative 2 to 2, union 2 to positive infinity. With example C, or part C on example 1, we take the denominator, set it not equal to 0. And what we notice here is that we can't square a number and get negative 1. So there is no exclusionary values on part C. So this domain is all real numbers, or we can just simply write negative infinity to infinity. And then finally for part D, we take the denominator, not equal to 0, solve for x, and we get x cannot be 1. So again, interval notation, or set notation rather, x cannot be 1. Or we can simply say that it is negative infinity to 1, union 1 to infinity. And that's how you find the domain of a rational function. When we talk about rational functions, one of the things too that we have to consider is that the function has to be in lowest terms. Graphically, we can determine a lot of things about these as well. But before we start getting specific about the graphs, let's just take a look at something that we might note visually about this particular graph, 1 over x squared, and then we'll discuss more about what the implications are with what's going on with this particular graph. So the first thing we notice, it is rational. So let's find the excluded values from the domain. So we have x squared cannot be 0, which just simply implies then that x cannot be 0. So the domain on this particular function is going to be all x such that x can't be 0. And graphically, what I want to do with that is I just want to draw a dotted line through x equals 0. Then we want to see what other properties we can ascertain about this graph. Well, one of the things that we've talked about before is when graphs are even or odd. So remember, if we take the function and we evaluate it at negative x, if we get the exact same function back, it's odd, or even rather, and if we get the opposite function back, it's odd. Well, in this case, when we square negative x, we get positive x squared. This is the exact same function that we started with. So we know that this is even. And what that means as far as the visual representation goes is that this graph is symmetric about the y-axis. So it's going to have kind of a mirror image across the y-axis. The next thing that I want to do is come up with a few test values perhaps to see what happens when we evaluate this function at some given values. So let's say that x is 1/2. When x is 1/2 and we evaluate this, we get 1 over 1/2 squared, which is 1 over 1/4, and 1 over 1/4 we know to be 4. When x is, let's say, 1/100th, when we take 1/100th and square it, we get 1 over 10,000. 1 over 1 over 10,000 is going to be 10,000. If we go the opposite direction now and start using some larger values, let's say x is 1. 1 squared is 1. 1 over 1 is 1. When x is 2, 2 squared is 4. 1 over 4 is 1/4. And then let's finally end with when x is 10. 10 squared is 100, so we get 1 over 100. So as our values get closer to 0, we notice that our y values are getting larger. And as we get further away from 0, going in the positive direction, we notice that our y values are getting smaller. So visually what this is going to look like is we're going to have these values get really, really close to the green line that we drew initially, because we can never have 0 in there. This graph will never make it to 0. And then the same thing is true going out in the positive direction as we move out to larger x values. They're going to get really, really small, but they're never actually going to be 0. We can't divide a number and get 0 as a result. So it's going to approach the x-axis as it moves out to the right. And if we're moving from right to left, it's going to approach the y-axis, but never actually cross the y-axis. And because we established what we've written there in pink, that this is even, then we know it's symmetric. So the left-hand side of this graph is going to be the mirror image of that function. And so this is what your graph of 1 over x squared looks like. Now you don't have to go into all this detail. I'm just trying to explain this. These you can absolutely graph on your calculator to get an idea of what the graphs look like. What we're doing with example 3 is we're just transforming the graph that we found in example 2. And this -2 shifts that graph right 2 units. And this +1 shifts it up 1 unit. So we just take the graph that we have here in our previous example, and we shift it right 2 units and up 1 unit. So I'm going to use some green dotted lines to represent the transformations here. I'm moving the vertical asymptote, that's that green dotted line that we drew initially, 2 units to the right. And then the x-axis was a horizontal asymptote, and I'm moving that up 1 unit. So I've split this graph again, and I just draw my graph that we had before. And that just simply represents the transformation. Again, calculator will make this one a whole lot easier to do. I'm just trying to get through these to give you an idea of what's going on with these transformations, how these graphs work. And that green dotted line is important because that's what we're getting ready to talk about next. The green dotted line, in both cases, vertically and horizontally, are what we call asymptotes. They are an imaginary threshold, if you will, that the graph will not cross. We're also going to introduce a concept of something called an oblique asymptote, and that's kind of it's also called a slant asymptote. And you can probably determine from that name that it is it's not a vertical or horizontal line. It will have some kind of a slope to it. And we're going to find easy ways to come up with the equations for these asymptotes. So a vertical asymptote, you just simply look at the denominator of the rational expression. If there's a value you exclude from the denominator, from its domain, then if you just simply put x equals in front of that number, you have a vertical asymptote. The graph will not cross that line. If we wanted to find vertical asymptotes, like I said, you would just find the exclusionary values of the domain and then write an equation using those exclusionary values to come up with the vertical asymptote. So let's just look at this example 4, and that should hopefully make more sense to you. We take our denominator, and it's not equal to 0. And when we solve this, we get x is not equal to 1. So that means our vertical asymptote is actually x equals 1. For part B, x squared minus 4 not equal to 0. And we get x squared not equal to positive 4. And x can't be plus or minus 2. So our vertical asymptotes, we have 2 in this case. We have x equals negative 2 and x equals positive 2. These are the equations of those dotted lines that I drew in examples 2 and 3. For part C, x squared plus 1 not equal to 0. This is similar to one that we saw at the very beginning of these notes. We get that x squared can't be negative 1. Well, there's no negative values that we can square, or no values that we can square to generate negative 1. So this one has no vertical asymptote. And then for part D, this one's a little bit different because one thing we note is that this function may not be in lowest terms. We cannot make any determination about asymptotes unless the function is in lowest terms. The numerator is the difference of two squares, so we know that that factors into x plus 3 and x minus 3. We also note that the denominator factors into x plus 7 and x minus 3. Now, we're strictly speaking about vertical asymptotes, not the domain. So with vertical asymptotes, when we cancel these two terms, we're left with x plus 7 in the denominator. And what that will lead us to conclude is that x equals negative 7 is a vertical asymptote. The domain on part D would actually exclude the values for positive 3 and negative 7, but we only have the vertical asymptote at negative 7 because the function has to be in lowest terms before we can make any determinations about a vertical asymptote. Here are some examples of vertical asymptotes and how they are, how the graphs are affected by them. You can see in each case the graph does not cross that vertical asymptote at all. It approaches it. The graph has different end behaviors as it gets closer to that asymptote. It just all depends on what the initial function is. Here's where we kind of have to look at some analysis a little bit, nothing really complicated, but we're talking about horizontal and oblique asymptotes. And so I'm going to go ahead and just skip to this part right here where we have the note that kind of breaks down how we figure this out. For horizontal and oblique asymptotes, you have to look at the degree of the numerator compared to the degree of the denominator. If the degree of the numerator, this is note 1 right here, if the degree of the numerator is less than the degree of the denominator, then you have a horizontal asymptote of y equals 0. If the degree of the numerator is equal to the degree of the denominator, then you just take a ratio of the coefficients in front of those two highest degree terms, and that's your horizontal asymptote. If the degree of the numerator is 1 more than the degree of the denominator, you have to use long division, and then you can come up with the equation for the oblique asymptote. And if the numerator is greater than the degree of the denominator plus 2 or more, then there are no horizontal or oblique asymptotes. And I promise these will make sense when we go through these examples. I have at least one of each as we go through here. So for example 5, it says find the horizontal asymptote if one exists of the graph r of x equals 4x cubed minus 5x squared plus 2 over 7x to the 5th plus 2x to the 4th minus 3x. Well, what we need to look at is simply the degree of the numerator compared to the degree of the denominator. The numerator, the degree is 3. The denominator degree is 5. Well, 3 is certainly less than 5. Let me indicate this is the numerator. This is the denominator. So if you go back to that red box on the previous page, you'll note that if the degree of the numerator is less than the degree of the denominator, you have a horizontal asymptote at y equals 0. And that's all you have to do. For example 6, same thing. We're going to find what the horizontal asymptote is of the given expression. The degree of the numerator is 4. The degree of the denominator is 3. And what we have is the numerator is 1 more than the degree of the denominator. And when you go back up to the notes that we had in that red box, note number 3 indicates that if the numerator is equal to the denominator plus 1, then we have an oblique asymptote. So we have to do polynomial long division. We've looked at synthetic division, but in this case we have to do the long division because we're going to generate a new equation in the quotient itself. So let's take x cubed minus x squared plus 1, and we're going to divide it into our function 3x to the 4th minus x squared. Now we want to have every power represented, so it has to go in descending order of powers. We do not have an x cubed term, so we'll just put 0x cubed. We have our x squared term. We do not have a linear term, so plus 0x, and we don't have a constant, so we'll put plus 0. We've not changed the value of the function at all. We've just rewritten it to make the division a little bit cleaner as we go. So x cubed into 3x to the 4th is going to be 3x, because 3x times 3x cubed will generate 3x to the 4th. And then we just multiply every term in the divisor by 3x. So we get 3x to the 4th. Let's see, minus 3x squared plus, that's 3x cubed, sorry. Make sure I'm doing my multiplication right, guys, before I go on. Okay. And then it's going to be plus 3x. Now keep in mind with long division, we're doing subtraction of this line, so we need to change all of our signs. And these terms cancel. We get 3x cubed minus x squared minus 3x plus 0. And then we do the division again. X cubed into 3x cubed is positive 3. Multiply the divisor by positive 3. And again, we're subtracting, so change the signs. These cancel. We get 2x squared minus 3x minus 3. And then here we note that we cannot divide any further because x cubed will not go into 2x squared. But all we're interested in is our quotient, which generates the equation for the oblique asymptote. So the oblique asymptote in this case is y equals 3x plus 3. With example 7, we note that the degree of the numerator is 2. The degree of the denominator is also 2. So these are equal to one another. And when you refer back to the red box there, 2 pages up on page 5, where it talks about finding horizontal oblique asymptotes, note number 2 indicates that if the degrees are equal to one another, then we just simply use a ratio of the coefficients. So our horizontal asymptote is y equals the coefficient on x squared in the numerator is 8. The coefficient on x squared in the denominator is 4, and that simplifies to 2. So y equals 2 is our horizontal asymptote. And I believe this is our last example. We are looking for the horizontal oblique asymptote, if it exists, of 2x to the fifth minus x cubed plus 2 over x cubed minus 1. So the degree of the numerator here is 5. The degree of the denominator is 3. Going back to the notes on page 5, the note number 4 says that if the degree of the numerator is 2 or more than the degree of the denominator, then there is no horizontal or oblique asymptote. And here we note that the numerator is exactly 2 greater than the degree of the denominator. So this one has no horizontal or oblique asymptotes. And that's all you have to do on this. So your homework is, or your suggested problems, I do think that it would benefit you to go through a few of these just to make sure you understand how to find everything. And let's see, there's only 14 questions, so it wouldn't actually really take that long. 1 through 6 are very similar to what we did with the first example. 7 through 12 are what we've pretty much done here with the last few examples. And then 13 and 14 are kind of applied problems that make these a little bit more tangible and relatable to real-world applications. So I hope everybody's doing very well. We will plan on having 2 Zoom classes next week as opposed to the one that we had this week. We'll try to get 2 in. Just really looking forward to seeing everybody. Had kind of a low turnout yesterday, so we'll try to get that up, and I will be talking to you guys soon. Everybody have a wonderful day and a great weekend.